Hi everyone, this is James from the University of Minnesota Chemistry Department, and we are here with our last video on our electronic structure program where we are going to finish up the code to convert our Hartree Fock program into a density functional theory program. Okay? So rather than what we did for the past few videos where we went through and we line type, in this video I'm just going to show you and highlight some of the changes, and then of course all of the MATLAB code for this will be posted on my website at www.chem.umn.edu/johns, and I'll put a link to that in the comment section down below. Alright, so here we go. We are going to finish our program. Alright, so we'll start by looking at how the program starts. Originally, the program that we had running it was called HF driver, and now we're going to change it to DFT driver. And if we go back and look at our original program, the only thing that changes is this one line down here. Minimum energy, we're going to change it to DFT underscore SCF. Right? So we're going to do a DFT SCF loop. And so let's see how that loop is going to change. That's the first file we really need to look at. Right? This is kind of a long file, but you'll notice most of this all the way down to here looks the same except for one line. This phi a, this build basis functions. We need to build our basis functions in real space so that we can evaluate the exchange correlation potentials. Alright, so the parts that change are build basis function. We need to write that function. That's a new function. And then a whole lot down here in the actual SCF loop. And we're going to change build exchange Coulomb to build Hartree. So we're only going to look at the average Coulomb potential. Then we need to build our density. Given a density matrix and our basis functions, phi a, we need to build our electron density on a grid in x, y, and z. And so this function build rho is going to take in our density matrix, our location of our atoms, the number of electrons we have, our total basis functions, and give us out the density at x, y, and z in a grid of x, y, and z points. We're going to get our x, y, z grid out. Okay. The next function, build exchange, which we also have to write, is going to take in our density in our grid and our basis functions, and it's going to spit out our matrix representation of the exchange potential. And then build correlation is going to do the same thing, but for the correlation potential, right? So we're going to get, these are going to be the size of the number of basis functions squared. We're going to then build our Fock matrix, and our Fock matrix is going to be our initial Hamiltonian, our core Hamiltonian, our electron-electron repulsion, our exchange potential, and our correlation potential. And so we don't need to write anything new here. And then the final piece that's new is down here, the energy. To evaluate the energy, we're going to do the Fock energy, which is the same way that we did, same thing we did for the Hartree Fock program. But now we need to also include evaluating the exchange correlation energy. And to do that, we need to write a program that takes in the density and the spacing of the grid, and we're just going to integrate the density times the energy density for the exchange correlation functionals. Okay, so let's go ahead and get down to it. Let's look at this first one. Phi a equals build basis function of basis. All right, and so what this is going to do is we're going to loop over the number of basis functions that we have. So we're going to loop over each basis function. For each basis function, we're going to get how many Gaussians we have in that contracted basis function. And then this is where we get a little bit of MATLAB programming stuff. We're going to build what's called an anonymous function. And this is going to take our x, y, and z location and give out the basis value of that point. And so for each Gaussian, we're going to make a Gaussian in x, a Gaussian in y, and a Gaussian in z with the correct exponent and the correct location. We're going to multiply them together times ax times ay times az times our normalization constant times our contraction coefficient, and we're going to add that back to phi a. Right? So we're going to say phi a is an anonymous function that equals phi a plus our new Gaussian function added in at the appropriate level. We're going to loop over each Gaussian, each basis set, and we're going to get a cell structure that's going to have all of our basis functions. Okay. Let's go to the next function we need to write. Build Hartree. This one should look really familiar. This is exactly 1/2 of the build Coulomb exchange function that we wrote for our Hartree Fock program. The only difference is this line highlighted here, where we're looking at just the average electron-electron repulsion. Right? So we're taking our force center integrals. We're taking, we're just looking at half of those force center integrals that we used before. Okay, build rho. The next function we need to look at is the one that builds our density. And this is going to take in our density matrix, our list of atoms or locations, the number of electrons we have, and our anonymous basis functions. Okay? And we're going to build a grid. And I just built this grid to be 8 Bohr larger than the dimensions of our atoms. So if our atoms are at 001 and 002, minus 1, 00 minus 1 and 001. So they're 2 Bohr apart in the z direction. Then our box is going to be 8 Bohr in x, 8 Bohr in y, 16 Bohr in x, 16 Bohr in y, and then 18 Bohr in z. Right? So that plus 8 on the right, plus 8 on the left, and then the 2 in between. Okay. So that's all we're doing here is setting up that box. Mesh grid is a function that will allow us to put out a grid in x, y, and z. This is a special built-in MATLAB function. We'll initialize rho to be the same size as x grid, but all zeros. And then we're going to add to it, we're going to loop over each of our basis functions and multiply 2 times the density matrix element of ij times basis set I times basis set j at x, y, and z. Okay, and that'll give us our looping over all of our basis functions. That'll give us our density in x, y, and z, and we'll output that as part of the function. So now all we have to do left is build our correlation, build our exchange potential, build our correlation potential, evaluate the exchange correlation energy, and then we're ready to actually try and see if this program works. Okay, build exchange. Build exchange is really easy. We're just going to use the Slater exchange or Dirac exchange. All right, so remember we're going to take build exchange. We're going to take our density input, our grid, and our basis functions. We're going to have our spacing on the grid is 0.05 Bohr. Remember we're going to have this RS. This is the radius at each. This is the value of the radius of a sphere of density rho evaluated at each point in space x, y, and z. And now we're going to loop over each of our basis functions, and we're going to evaluate the integral over phi I at x, y, and z times our exchange correlation density, our exchange correlation potential, which is just 3/4 times the exchange correlation energy, times phi j. And it's sum over all of those, sum over x, sum over y, sum over z, multiply it by dx cubed. So we're just doing Riemann sum, and that will be our exchange potential matrix. Let's go to the next one. Build correlation. It's a little bit longer. Same idea as the exchange matrix, just the mathematical form for the correlation energy density and correlation potential is a little bit larger. So again, we're going to take in our density, our grid, and our basis functions. We'll calculate the radius of spheres with density rho. We'll have x equal to the square root of that. We're going to take in 4 parameters that are fit from the VWN paper. And then we'll calculate these auxiliary functions. Capital X is this polynomial x squared plus bx plus c. X underscore x naught is x evaluated at x naught, which is one of our fitted parameters. Q is just square root of 4c minus b squared. The energy correlation has this long form. Right? It goes all the way across here and down to here. The correlation potential is the energy correlation energy density, the correlation energy density minus 1/6 of this function of the same polynomials, right? So remember that's the density times the derivative of the correlation energy with respect to the density. And then we're going to do the same thing we did for the correlation, for the exchange energy, which is we're going to get our matrix elements for the correlation potential matrix. And to do that, we're just going to integrate over phi I times our correlation potential times phi j multiply it times dx cubed. So we're just going to take that Riemann sum. Okay. Last thing we have to do is evaluate our exchange energy and exchange correlation energy. And now all we need is just the density and the grid spacing. Right, so again, we'll calculate this auxiliary function Rs. Our energy this is just going to be the integral over all space of the density times the exchange correlation energy density. So we'll then take the sum over all space minus 0.4582 times the density divided by our radius function, sum over all of that cubed, and that's our exchange energy. Pretty straightforward. For our correlation, again, we're going to build these auxiliary functions. We'll write down a functional form for our correlation energy density, and then we'll integrate, or Riemann sum, our density times our correlation energy density times grid spacing cubed, and then the total exchange correlation energy is E is the exchange energy plus the correlation energy. And that's it. That's all that we need to change for our Hartree Fock program to turn it into a DFT program. So now let's see if that works. Let's see if this whole thing works. Okay, so we're going to try the same example that we tried earlier. We're going to have two hydrogen atoms. Our Z is going to be 1 and 1. We're going to have them be separated by 2 Bohr. And so let's go hop over to MATLAB. Whoop. All right, let's do this. Z equals 1, 1. Atomless equals 0, 0, minus 1, 0, 0, 1. And then, let's see here. DFT, make sure I get the right one. Should be DFT driver. Z, comma, AL. All right, we'll let it go. Still going. Still going. All right, we're going to let this go for a little bit. Whoa, it's done. It's done. All right. Okay, so that took, that took 2,517 seconds. Ooh, man, that took forever. Okay, but we got an answer, and the answer minus 1.138 is the same answer that we would get if we used Gaussian or some other electronic structure calculation package. So, you might be thinking, why on earth did that take so long when the Hartree Fock went so fast? And the reason is it's the integrals over for the exchange correlation potential. And the way that we set those integrals up was really slow. If you would actually go back in and look at the number of points, we had a grid that was something like 400 by 300 by 400 point. 400 by 300 by 300 points, right? So that's, let's see here, 90,000 times 400, 3.6 million points. It's a really big grid, okay? And just storing all that in memory and doing calculations on that grid is just massively time consuming. Now there are other ways that we could do that. One of the original paper from Beck back in the late 80s, early 90s set up what's become to be the standard, which is to have a set of grids centered on each atom, okay, and have a radial grid. And then that's what Gaussian and all the other atom-centered DFT packages do. And there you can get the same level of accuracy, but maybe only use 99, or let's say 100 times 30,000 points. Okay, you can do it with way fewer points, and that makes for a big difference in terms of speed. And so reprogramming it in MATLAB, and the fastest I've been able to get the H2 molecule to go is around 10 seconds. So about a factor of 200 better than this. which is about a factor of 5 to 10 slower than the Gaussian program, or what I would expect it to be if I wrote it in Fortran. So that's where that is. I will obviously I will post the code for this on my website. I'll also post the code for the faster version with the atom-centered integrals, although I probably won't make a video out of that. I'll at least post that code so you can take a look at it. Hopefully this video series has been helpful to you. It helped you increase your understanding of how electronic structure codes work, and what they actually do, and what DFT actually does, as well as Hartree Fock. Please leave any comments, questions, suggestions in the comment section down below. Hit the like button if this was helpful to you, and hopefully if you like this, I will make more videos, and I will see you later.